All right, section 9.9. Today we're going to talk about representation by power series. So we started talking about power series in 9.8, right? So we're going to continue that discussion today. So we're going to consider a function, specifically f of x equals 1 over 1 minus x. This closely resembles the sum of a geometric series. So the sum of a geometric series, if you'll remember, is this right here, a over 1 minus r. That looks very similar to 1 over 1 minus x. And a over 1 minus r came from the summation n equals 0 to infinity of a times r to the n, as long as the value of r was between 0 and 1, the absolute value of it anyway, so between negative 1 and 1 in total. So if we were to do some correspondences, right, where we let a be 1 and r be x, we could actually take that summation from n equals 0 to infinity, replace the a with 1, replace the r with x. We'd have the summation from 0 to infinity of x to the n, which is the sum of the power series, like 1, x squared, x cubed, and so forth. And this would actually equal the 1 over x, right? Because that's a over 1 minus r. A is 1, r is x. And this would hold as long as we are between 0 and 1, or the absolute value of x is less than 1. But this would only work then on the interval, negative 1 is less than x is less than 1. If the series were centered somewhere else, we would need to develop a different series entirely. So this is only going to work if we're centered at 0. And I know this doesn't say centered at 0 anywhere, but it necessarily is. Otherwise, the interval would not be going from negative 1 to 1, the center of that being 0. Okay? So somehow we can make this correspondence that turns something into a geometric series. That's what we're doing. Okay? So we're looking for a way to change an expression, if possible, into something that looks geometric. The sum of a geometric series. And that's not always possible. So this doesn't work all the time, right? It's not a catch-all. But it does catch some things. And the ones that it catches, it works really nicely for, okay? So we're going to talk in a little bit later about what we do when it doesn't have this form. But let's see one that does have this form first. Okay, so this does not say a over 1 minus r like the other one did, right? In particular, I really need this right here to be a 1. That's the kicker. I have to have this say 1 in order to use this. So what would I have to do? Well, and it has to be centered. This one is centered at negative 2. Okay? So we're going to look in this one at what happens when the center is a slightly different value than the original one we just saw on the previous slide. Okay? So let's start with where the center is and figure out what needs to have happen. So what I need is I need this piece to be a 1, like I mentioned. So that's going to be one of my goals in the process here. We're not going to deal with the 6 directly because it's just going to change slightly before we get there. And this piece right near here has to have a value that shows that it's centered at 2, not centered at 0. If it's just left as x, we would be centered at 0. So I need it to say x minus 2 because that would be centered at 2. Okay, do you see what the goal is? The goal is to get the first piece to say a 1 and the next piece to have the piece around which it's centered. Okay? So let's take a look at what we do in order to get that to happen. Okay, so we have our f of x. It is 2 over 6 minus x. And I'm going to introduce a change to the denominator that just changes its form. Instead of it saying just x, I want it to say x, hang on, sorry, this should say x plus 2. I apologize, I thought it said centered at 2, but it said centered at negative 2. So this should say x plus 2. Centered at 2. Negative 2 is x plus 2. There we go. So this needs to say x plus 2. But you can't just go adding 2 to a denominator. And in reality, I didn't even add 2 to this denominator. I subtracted 2, didn't I? Yeah. So I need to compensate for the fact that I introduced a negative 2 into this expression in the denominator. How would I compensate for that?
Doesn't work, you just do the denominator, right?
Nope, it wouldn't be something about the numerator. We just need to add 2 to the denominator, yeah. So I've subtracted 2 to the denominator because there's a negative here, right? So that's negative 2. And this is the compensation. It's kind of like when you do completing the square. You remember that process? where you either add the same number to both sides or whether you add and subtract it to the same side if you're trying to look for like a vertex or something like that. This is what we're doing. We're making an adjustment to the denominator and how it looks because I need for it to actually have an x plus 2 after that negative sign. So this is my adjustment. So when I make this adjustment, now I have, oh, it's still a 2 on top, sorry about that, a 2. The 6 at the beginning, the 2 at the end makes 8. And I have x plus 2 here. So the first thing to adjust is the centered, where it's centered, which we've adjusted. Now I need that 8 to be a 1. How do I fix that?
Multiply by 1/8.
Yeah, so we're going to multiply by 1/8. Of course, it'll affect other things, but it'll fix the 8th problem. We'll talk about how it changes everything else, and it's okay that it does. But it fixes the fact that I had that 8 at the beginning. So now I have 1/4 over 1 minus, and my x plus 2 is now divided by 8. Okay, so I'm going to flip back a screen. What we did here then is that we made an association, right? We associated a is 1 and r is x. We need to do the same sort of thing here. What would a be if this is a geometric series? 1/4. Remember, our series needs to be matching up to this, a over 1 minus r. So my a is 1/4, and what's my r?
X plus 2 over 8.
Mm-hmm. X plus 2 over 8. Okay, everybody good? All right, so what does that mean? Well, it means that I should be able to take this expression, because this is now the a over 1 minus r, and put it back into the summation formula where the a and the r came from. So a was at the beginning, right? So again, I'm trying to mimic this. In fact, I'll shift it over here and show it. This needs to go back to being correspondent to a, the sum from n equals 0 to infinity of a r to the n. Okay? So the a value, 1/4, goes at the beginning. The r value, the x plus 2 over 8, goes next to the power of n equal 1 to infinity. Not 1, sorry, 0. N equals 0 to infinity. There we go. But there is something that we shifted when we did that, right? Or that we have to consider or remember when we do that. This doesn't always, that is, the summation does not always equal a over 1 minus r. There's a condition for which that's true. What's the condition that has to hold for this to be true?
It has to be between 0 and r has to be between 0 and 1.
Yeah, so this absolute value of r has to be less than 1. They write it like this a lot of times too. And so it has to be between 0 and 1. Obviously, it's just saying that it can't be equal to 0, right? That's what that's telling you. All right, so we need our value to be between 0 and 1. But what's our r value?
X plus 2 over 8.
Right, so it's, for us, x plus 2 over 8 that needs to be less than 1. So we have to find where this is actually true for, because it's not true everywhere. It's only true if this inequality holds. So we did this last time where we set up a triple inequality. Remember that? -1 is less than x plus 2 over 8 is less than 1. And then what happens?
Wouldn't it be 0, you said?
We just need to make sure that it doesn't equal 0 in a minute.
Okay.
So in other words, x can't be -2. That's a condition we'll deal with. But what was that?
-10 is less than x. X is less than 6.
Okay, so first we would multiply by our 8, so -8, like this. And then we would shift by subtracting 2. So we'd have -10 is less than x is less than 6. And it is true that x cannot equal -2, because that would make that 0. That's as well, a condition as well. You don't see them usually listed that. I'm not exactly sure why. They sort of just gloss over that piece for the most part. So if you're checking backs of the books or things like that, you're probably not going to see that. But this is my interval in inequality form, or we would say see it written as negative 10 to 6 for the interval that way. Okay, so this is obviously very specific, right? I mean, not everything is going to be an a over 1 minus r form. Yeah.
Would the interval not be to 2 and then union 2 to 6?
Yeah, so they don't end up including it like that. I don't know why. I should probably research that because as I'm just sitting here and thinking about it and Adeline's asking me that question, I've never seen them do that before, but I don't know the answer for the why.
Okay.
So this,
like if
we'll
we
leave
go-
this as a question mark for me to look at for you because I'm not sure why they don't actually split that interval up. Yeah.
Homework, do you want us to include that equals 0 in some instances?
Don't worry about it. There's got to be a reason it's not included. I just don't know what the reason is.
Got it.
Yeah. So you're just going to be worrying about the fact that it's negative 10 to 6.
So the WebAssign won't like freak out if we do
It
that.
shouldn't. Mm-mm. No. Yeah. Okay, so this is great as long as it has a form that looks like a constant on top and then a constant minus the variable on bottom, right? We can do some shifting like this. Yes.
And then I wanted to double check, we said our goal was to make an x be an x plus 2.
Yes.
And then whenever we made the 601, or the,
Mhm.
the 601, it became x plus 2 over 8. It's cool that it's divided by 8 so long as the x plus 2 is present. Is that correct?
Yes, correct, because that's the shift that we needed to have happen. Right. Yeah. Okay. So some operations with power series, and then we're going to look at general power series. So operations with power series do a lot of the things that you would expect. So if we have two summations, so we have two power series, f of x is the summation from n equals 0 to infinity of a sub n x to the n, and g of x is the same but with b sub n. They're otherwise the same. So they have the same summation, starting and ending points, if you will. And so if we take a constant multiplier, think about what happens when you have a constant multiplier, and you multiply it by x, it's like taking and replacing the x here with kx. So therefore you have k to the n and x to the n. Make sense? Distribution of exponents kind of property. The second one is actually another property of exponents. If you have x to the capital N, they're using capital N here as a constant. I don't know why they don't just use a different letter used here. I don't know. Like, why didn't they just use a C? I'm not exactly sure, but this is what they've used. So you've got the number n, like as an actual number. Then x to the n gets replaced, very much like having now x to the n, and you've got property of exponents that says I can multiply those powers together. And the last one says if we add or subtract them, then it's the same as adding or subtracting the a sub n and the b sub n. Now, when we do add and subtract, potentially, the two different power series, it's possible that they don't have the same interval of convergence to start with. Right, so if both of them are interval of convergence negative 1 to 1, or like what was it, negative 10 to 6 or whatever, then that's fine. But sometimes they don't actually match. For example, this is not a real like full out example, but just to show you about the interval of convergence. On the first one here, this is the same power series that we started with this morning, the summation from n equals 0 to infinity of x sub n, and it converges from negative 1 to 1. Okay, that's fine. The second one, however, is divided by 2. So if you think about what happens when we set that up to being absolute value less than 1, you're going to end up multiplying the 2 to both sides. So this one's interval of convergence is negative 2 to 2. So this one has a bigger interval of convergence. Now, they won't necessarily be nesting like that, where one of them's little and the other one just encompasses it. They could simply be like overlapping pieces. I'll talk about that in a moment. But the answer for what's the interval of convergence for the sum when you add them together is what they have in common. Okay, it's the intersection. In this case, the intersection is actually negative 1 to 1. So that's easy because they're nested, right? One's embedded inside of the other one. But pretend for the moment that you had something that was overlapping so that it looked like, I'll do in different colors. One of them looked like this, and the other one looked like this, right? So they overlap each other. Then the interval of convergence would be the overlapping piece. It's always about it being the intersection of what we're looking for. So they could be embedded, but they wouldn't have to be embedded for this to work. Are you with me on that? Okay, so we have to pay a little bit of attention to our intervals of convergence when we work with summations. So let's take a look at one. Okay, so there's lots of things happening in this section. One of the things happening in this section is that you're going to see some of them that they don't have the form that we want. Like this does not say a constant on top and then a number minus x on bottom, right? It doesn't quite have the form of a geometric series. It doesn't, the sum of a geometric series. But if we use partial fractions decomposition, then we would be able to do that. Now, there's not many questions that are like this, and I don't need you to do the partial fractions decomposition. The ones that are assigned that have this will give you the decomposition and you move forward with it. So that's good, right? We don't have to find what's on the right. It's given to us in the problem, okay? But as we're taking a look at this, we're going to do what we had done on the previous one, but we're going to do it all full out. So this is kind of a combination of the things I did here and the checking the interval of convergence here. Okay, so starting out with this one, and again, we don't need what's on the left because they've actually decomposed it into what's on the right here and here. So we're going to do each of these pieces separately. I have 1 over 1 plus x. Okay, so I need for this to look like, let's see what I had done before. Where was my form? It was a over 1 minus r, right? I need this to be in the form a over 1 minus r. And it's not far off. What's not quite right?
It's adding instead of subtracting.
It's adding instead of subtracting. So I really do need it to be changed. It really needs to say a subtraction sign here. So how do I accommodate for that?
Parentheses, add a negative.
Yeah, I just changed it to be minus a negative x. Right? That's fine. So at this point, I can identify what's my a and what's my r. So what is a? 1. And what is r?
Negative x.
Negative x. So far, so good? Okay. So I'm able to, and again, I should have written these at the top so that we can keep referencing them. This is ar to the n, 0 to infinity. Okay. So my a value can be changed then, or can be written in then. Whoops, that's not what I meant to do. This is as 1. And my r value is negative x to the n. So n equals 0 to infinity. Okay, so there's nothing wrong with the way it's written there, but it's not exactly the way we normally would see negative x to the n. You know, that's not how we normally would see it written inside of a summation. Do you know what you would do to adjust it to look more like the things we've been doing in sections 9.2 through 9.6? What do you think?
You would pull out a negative 1, put it to the n, right? And then just leave x to the n.
Yeah, so we would take this and we would rewrite it. Instead of it saying negative x to the n, it can say negative 1 to the n and x to the n. So it would end up, like Alex said, looking like this. And remember, that's just property of exponents that allows us to do that. And this actually looks familiar now, right? What kind of a series is this?
Alternating.
It's an alternating series, okay? All right, so we're going to come back to this in a moment. Let's just hold tight for this one. This is what we needed it in. We needed it in a form that we could use. We're going to use it in a moment. But let's do our other. Move this, make this smaller. Let's do our other of the two that we were given to begin with. So the other one is the summation. I'm sorry, not summation. It's 1 over 1 minus x. Okay. What's wonderful about this one?
It's already ready.
It's already ready for us, exactly. What's A?
1.
1. And R?
X.
X. In fact, this is the very one we started with this morning, right? It's exactly the same one. So this is summation from n equals 0 to infinity of 1, if you wish, and then x to the n. Or just leave the 1 off if you wish to. Okay. So what we're supposed to be doing then, back up to the original problem, is turning each of them individually into summations, which we have. And then we're going to put the summations together. That's property number 3 down here, right? I should be able to take each of them individually, and then in our case it's subtraction, and I can subtract the summations that we have. So we can rewrite them. This is the sum from n equals 0 to infinity of what do we have? -1 to the n, x to the n, and then minus the sum. Yes.
On our paper, it has it as a positive between the two.
Oh, it does. Do I have it negative on my screen? I do.
Yeah.
I think it's supposed to be positive. Yes, I think it's supposed to be positive. I think I fixed it. This is why I told you guys I usually do this and then I go back to it, and I fixed it on my paper, but I forgot to fix it on the screen itself. Okay, thank you for that. Yes. The summation from n equals 0 to infinity of x to the n. All right, that's correct. Thanks for letting me fix that, you bet. All right, so we'd like to be able to combine these together, right? And over here, what I'm told is that I can combine them together. They've got the same index summations, right? 0 to infinity. They both have an x to the n in them. And I can take the series pieces, right? The summation pieces, and I can add, or in this case it is addition, I can add them together. So I can take this and I can rewrite it as one larger series. And the larger series is -1 to the n plus the 1, and then all of this is times x to the n. So I'm taking the coefficients of each of those summation x, those x to the n pieces, and I'm pulling them out, and I have -1 to the n plus 1, and then I have x to the n. Now, there's no concise way to rewrite that when we see it in this form right now, but there will be if we write a few terms out. So at this point, algebra-wise, I can't factor this and make this look very clean. I mean, there's not a good way to do that. But what we're going to do is we're going to write out a few of the terms. Okay, so I want you to work with me. If n is equal to 0, what's going to happen?
It's 1.
It's going to give me a 1. Sorry, how do I want to write this? I don't have it written on my paper, is my problem. N equals to 0. I'd have -1 to the 0 plus 1 times x to the n. So the -1 to the 0 is the 1 piece. I think that's what you guys are telling me. Is that right? Does that help you? Look at that part in there. Hang on. Got a 0. There, n 0. I got them all in, all right? Okay. -1 to the 0 is 1. Plus the other 1 gives me 2. So this isn't 1 total. It's 1 in that little piece, and then I got 2 total. And the x to the 0 is 1, so I've got a 2 here. What happens when n is equal to 1? This is 0. -1 to the 1 is 0. And then the 1 is 1. So this becomes a -1 and a +1, which is 0. So I've got zeros here. What about when n is equal to 2? That'll be there, but I need something else from here. This will be a 2. Okay? So I have 2x squared. I'm going to write out 2 more of these, by the way. N is equal to 3. What will this one give me?
0.
That's another 0. One more, and I think we can pause enough to know what's going on. I have -1 to the 4th plus 1, x to the 4th. What's -1 to the 4th plus 1?
2x.
A 2. Okay. What's happening to the coefficients? Just look at the coefficients. 2, 0, 2, 0, 2, 0, right? Good. They're not doubling, but they're always 2s, right? So I have a 2, and then it becomes 0. And then I have a 2, and then it becomes 0, and then 2. They're oscillating between 2s and 0s, okay? Half of them are 0s. In particular, half of them aren't there. Which powers of x are missing? The odds. So I can rewrite this to represent what's actually there. I think I need a little more space. Let me shrink this. I didn't mean to grab that silly line. Okay, I'll move it in a minute. Here we go. Okay, so we have 2 is a constant. It's happening all the time. but we only have the even powers present. How can I make the exponent so that it's going to give me only even powers?
N plus one,
Nope. 2n.
2n.
Yeah. N plus 1 will sometimes give me odd powers. It depends on what n is. Sometimes it'll be even, some will be odd. 2n will give me only even powers. What if I wanted only odd powers? What would I do?
2n plus 1.
Either 2n plus 1 or 2n minus 1, depending on where I wanted my summation to start. Either one could work, right? Yeah. So 2n will give me the even powers, which is what I'm looking for here. And I need to make sure that it really will, in fact, start at n equal to 0 and go to infinity. So you have to double check your starting and ending point sometimes to make sure that it's going to work for you. That's why, like, if it were odd powers, I said, do you want n plus 1 or n minus 1? Or 2n plus 1 or 2n minus 1? And I said, it depends. So if you put in n equal to 0 here, will you get 2? Like this. If you put in n equal to 1, will you get this one? Does it work? Okay, so we want to double, let's spot check. Make sure that you're not changing something that's just a little bit off, because it's easy to do. Check to make sure that it gives you what you're expecting it to give you. Okay, the other thing that we're asked to find is not just the series, that's part of the directions, but also to find what? The interval of convergence, right. So what is the interval of convergence for each of these independently over here on the left? It's based on my R values, remember. Absolute value of R has to be less than 1. Yeah, so in both cases, my R is just X this time, right? Or negative X either way. So on the first one, it's negative X is less than 1. So I have negative 1 is less than X is less than 1. Actually, if you want to put a negative X in there, you can. And then you can divide by negative 1, but when we divide by negative 1, it flips the signs, right? It doesn't give us very interesting things because it just switched it around to begin with. The second one actually set up already to be absolute value of X is less than 1, so negative 1 to 1. Right? So these are the two intervals of convergence, and they happen to match. So the interval of convergence for my function, or my power series that I created, is also going to match that too, because they overlap in exactly the same place. So the interval of convergence is negative 1 to 1. Where is it? Oh, that's fine. I think that's good with what I've written. So these are the two pieces of information that I'm asked to find here at the end. Okay. Yes?
Do we have to check the endpoints on this?
We do not need to check the endpoints on this. If you were to check, well, let me say why. Remember, the geometric series doesn't converge for the endpoints automatically, so that's why we don't have to check it. We will be checking some endpoints on some other things later. I don't know if it's today or if it's on Wednesday. But this one we don't have to because geometric series automatically eliminates that endpoint. Yeah. Okay. There is another method in this section for finding a power series, and it's integration and differentiation. And again, there's a lot of it set up for you. You're not actually asked to do too much of the work for finding the pieces. Just what happens afterwards. Okay, you ready? So the problem starts out with all of that. Okay, so you're not like given what's on the left and told to find what's on the right. It starts out with both sides. We're asked to find a power series and the interval of convergence. All right, so as we take a look at this, the left-hand side is actually written as 2 over x minus 1 cubed, which means we wouldn't have been able to do this with a geometric series very nicely, right? I mean, if we did, it would have to be through doing some integration, like some partial fractions. The partial fractions wouldn't be very nice, though, because I'd actually have to have a potential of an x minus 1, an x minus 1 squared, and an x minus 1 cubed to make that work. That's not going to work very nice. It's not going to flesh out and work with a geometric series as it is. But this is the second derivative of the value 1 over x plus 1. So the way that this works is we take what we know about the summation of 1 over x plus 1, which we've already dealt with today. And I'm going to rewrite these pieces. Notice these are not partials, they're actually d's, okay? So we actually have on the left-hand side, or on the right-hand side, this piece. We saw this in example number 2, okay? The one that we just did had this in it. It was the first half. Right, the first half of it is 1 over 1 plus x. So we know that this looks like this. So we're just going to change it into this right now because we've already done that. If you hadn't already done it, that's where you would start. You'd start by creating what we did already on the first half of number 2. So we've already done that. We're not going to do it twice. So what that means is that over here we have the summation from n equals 0 to infinity of -1 to the n and then x to the n. That's what it equals. Okay, so far so good. We've just made a substitution for something we already did. What we're going to do next is we're going to find some derivatives. So how many derivatives are we going to find? 2, because it says d2 dx2, right? It's going to be the second derivative with respect to x twice. That's what it's going to be. So as we take the derivative, think about what happens when you take the derivative of functions. Anything that's constant disappears, right? You know what I'm talking about? Like any constants go away when we take a derivative of functions. So if we do this twice, we've actually lost not only the constant, but we lose the linear term as well. Are you with me on thinking about that? So if you had, just for an example real quick, if you had something like x cubed plus 2x plus 1, if you take the derivative the first time, the plus 1 goes away. But if you take the derivative again, the 2x, which turned into 2, would also end up going away. You'd lose both the linear term and the constant term if you take two derivatives, right? Okay, it's really important to sort of recognize that because we are going to see something shift here that we haven't seen yet before. Our limits of, not limits of integration, our summation limits, the bottom and the top, are going to change. The bottom in particular will. So we're just going to do it once first, and then I'm going to leave this here because I'm going to have to do it one more time in a minute. So if you take the derivative of -1 to the n, we notice the -1 to the n just keeps flip-flopping, okay? So it's a constant multiplier. That doesn't get affected by derivatives, so it just gets to stay. It doesn't change anything. But what's the derivative of x to the n? Nx to the n minus 1. But because we've lost our constant, our summation will no longer start at 0, it will start at 1. And it's because of this losing the plus 1 at the end business. We lose the constants, so we lose the ability to start at 0. We're going to fix it later on, but that's why that's happening. Okay, we're going to take another derivative now. So the constant multiplier stays, -1 to the n. N is now a constant multiplier as well. So what's the derivative of x to the n minus 1?
N minus 1 minus 2? Or x to the n minus 2?
Right. Okay, so decrease to the power multiplied by the previous power, n minus 1. And again, because we've lost that constant on the end, when we take derivatives, this will start at n equal to 2. Okay, so it kind of looks like we're done, but we're supposed to have this in the form of n equals 0 to infinity at the end. We have to make an adjustment. So the adjustment that we make will eventually, not eventually, it will right now, lead to this starting back at 0 the way it should. But we need to fix some things in order to make that happen. We need to make sure that when we put in 0, we get the same thing as when we put in 2 on the other one. Okay? So what happens when I put the number 2 in up here? Well, it doesn't affect my -1 to the n. Let me put that in first. What happens when I put the 2 in right here, in here?
You get 2.
And what?
2 times 1 times x to the 0.
So if I put in the number 2, I get a 2 here and a 1 here, right? Everybody good with that? So I actually end up shifting it slightly by putting in the number 2. So what I end up needing to do is I end up needing to make the shift that changes the n to be n plus 2. and the n minus 1 to be n plus 1. I have to add that 2 back in. I'm off by 2. If I just change my 2 to a 0, I'm off by 2. So try it again down here now. If I put in n equal to 0, if n is equal to 0 here, what do I get? 2. And if n is equal to 0 here, what do I get? 1. I get the same 2 and the 1 by making that shift. If I take away 2, because that's basically what I did here, I took this 2 and I took it away and made it a 0, I have to add it back in over here. I'm compensating.
And now x is to the negative 2?
Oh, that's a good question. What is x going to be raised to? To the n. Yeah. So I've added 2 to each one of the pieces that had the n in it. It's probably worth noting that the reason it doesn't matter on the negative 1 to the n part is actually because evens and odds give us the same thing. I didn't say that right. All even powers give us a negative 1, or all odd powers would give us a negative 1, and all even powers would give us a positive 1. So that's why my shift didn't need to happen. So technically, could I have changed this n to also be n plus 2? Well, yes, but it doesn't change anything. There's no need to change it there because of the oscillating nature of the powers when you have even versus odd powers on a negative 1. Okay? So I don't have to adjust that at all. It doesn't change anything because it's already shifted twice. All right. What about my interval of convergence? Because that's part of the directions too. What was my interval of convergence when I started? Do you remember?
Negative 1 to 1.
Yeah, up here, my interval of convergence is negative 1 to 1. And once again, it happens down here as well. My interval of convergence remains the same. Whoops, OC. It's negative 1 to 1. Okay, all stemming back to the geometric series thing.
On the homework, can we just put RC negative
Mhm.
1? Do we have to say like, oh, it's the same?
No, Yeah, negative 1 to 1. Okay, last one for today. Just enough time to finish. Interval convergence, same thing. Power series interval convergence, but this one is actually integration. So again, they've told us the information that you see here. That's how your problem will begin, unless I messed something up in WebAssign. I checked it for sure on the written part. So if something messes up in WebAssign, send me an email, let me know. My intent is not for you to have to set it up. It's just for you to work through it after it's been set up. Okay? All right, so over here, I need the integral of 1 over x plus 1. Well, I know what the series is for the 1 over x plus 1. It's the summation from n equals 0 to infinity of negative 1 to the n, x to the n. Again, that came from example 2. All right, from example 2, I got that for free at this point because we already did the work. All right, so we will integrate this. What is the integral of negative 1? Well, I should say the negative 1 to the n again is a constant multiplier, so it just stays. What is the integral of x to the n?
1 over n plus 1 times x.
Okay, yeah, x to the n plus 1, and it's divided by n plus 1. Or written as 1 over n plus 1. Either of those are fine. But I integrated,
Plus C.
thank you, plus c. We need that. I know. So what we need to do right now is to solve for c. Okay? So we are going to solve for c. Oh, I left off my summation. Summation is n equals 0 to infinity. So I don't have to be careful about my summation starting point when I integrate. I do when I take derivatives. Okay? So we need to figure out what c is. Well, all of this is supposed to equal the natural log of x plus 1. So we're going to notice that those two things are equal. And we're going to fix something that's helpful to us. In particular, x equal to 0 is a helpful place to start. We're going to let x equal to 0. So if x is equal to 0, this is the natural log of 1, and it will equal the summation. Well, yeah, I mean, we'll write it out, I guess. N equals 0 to infinity of negative 1 to the n, 1 to the n plus 1 over n plus 1 plus c. Okay, so what happens here? What is the natural log of 1? 0. Okay, good. What happens right here?
It's 0 out.
It zeroes out. So what did we find out that c is?
Is that supposed to be a 0
Yeah,
in the numerator instead of 1?
Yes, thank you very much. It is supposed to be a 0. It should zero out. Thank you. Typos all over the place. Okay, so c is 0. Are we good with that? Got my x's, zeros everywhere. So c is 0. And so the natural log of x plus 1 is equal to the summation from n equals 0 to infinity of negative 1 to the n, x to the n plus 1 over n plus 1. And what about my interval of convergence? Negative 1 to 1. And we do have to be a little bit more careful with these than we did before. I failed to mention it over here in the last one. We'll go back to it in just a second. But when we're integrating and when we're taking derivatives, the interval of convergence endpoints can shift, and we might be able to include them. So there's a possibility of that. So we need to pay attention to see if that happens, okay? So if I were to use negative 1 in here, so if I put in negative 1 in here, what's going to happen?
It's over 0.
It's going to become a 0 on top, right?
It's also 0 on the bottom though.
Does it become 0 on the top?
Are you talking about for x, though?
Not for x. For, yes, for x, sorry, yes.
X becomes 1.
X becomes 1, so we'd have 1 over n plus 1. All right, so if we put in negative 1,
That converges.
then I'd have 1 over n plus 1. Does 1 over n plus 1 converge or diverge?
Average.
Diverges. Why?
It's over
It's
0.
term test.
It's not the nth term test. The nth term test actually would not be helpful because the limit does go to 0.
P series?
P series are a version of it, or like a harmonic series, right? So it's not going to converge for negative 1, but what if I put the number 1 in? What am I going to have?
X squared over n.
Nope. Let me just actually write this one out because this was the more interesting one. If you put in 1, what do you get on top?
Oh,
What's 1 to the n plus 1? 1. Okay, so this eliminates itself. It's unhelpful. So what kind of series is this? Alternating series. And when does an alternating series converge?
When it equals 0?
When the limit goes to 0. So we actually get the limit going to 0 instead of the summation going to 0. So for the alternating series for negative 1, it works. So if x is equal to 1, we have an alternating series. And the limit goes to 0. So for x is equal to 1, it actually will change from that parenthesis to a bracket. And I meant to show you this on the other one, so I'm going to flip back to it now first. But x is equal to negative 1 actually gives me 1 over n plus 1. And with harmonic series or a p series or something like that, you're going to see it go to 0. You're going to see it diverge because of the harmonic series. So flip back real quick to the previous one. The interval of convergence here really is negative 1 to 1. And the reason why is because if x is equal to positive or negative 1, either way, you have an alternating series. That's fine. But what can you tell me about this particular alternating series? It goes to infinity, right? Because on this particular alternating series, I have n plus 2 times n plus 1, right? Because this becomes 1 right at the end. This piece alternates, but this piece in the middle has a limit that's infinity. The limit of n plus 1 times n plus 2 is infinity, and the divergence test would make that diverge. So this is an alternating series with either -1 or +1, doesn't matter, where the limit as n goes to infinity is infinite. Or you could say it's just simply not 0, because what we actually end up having is n plus 1 times n plus 2, and you have the -1 to the n here at the beginning. And so when you take the limit of this, you end up going to infinity. So this is a divergence test. Well, not divergence test, but the alternating series test where the limit diverges. So it wouldn't work.